say y1 satisfies the differential equation. So in that case what you get? You get u prime is nothing but f1x u plus f2x into 2u y1 plus u square. In general, y1 is a known solution which is function of x. So what will actually happen? So you will have f1x into u, f2x, this is the function of x into u plus this. So this will be like a Bernoulli equation. So what will you get? So in general, this is a function of x. I am saying f3 of x. So it is, we will get f1x plus f2x into 2 into f3x into u plus f2x into u square, which is Bernoulli equation. Okay, and then you can solve it. I will take an example and then finish this differential equation last part. So if you have decreed differential equation, you have to identify what type of differential equation you are getting. If you get this kind of equation, which is called as decreed differential equation, and in that case, decreed can be converted to Bernoulli type differential equation to handle. I will give an example problem, which is y prime equals to y by x plus x cube y square minus x to the power 4. This is a recalculated differential equation. If you look at it, the function of x. See, for the Bernoulli equation, note down will be having only function of x, y has to be there. If these are there, if this is not there, this is a Bernoulli equation. So, what actually happens? We have to assume y equals to y1 plus e. And y1 is what? y1 is solution which satisfies the differential equation. What could be the solution? Can you guess? Simple solution which will satisfy. Simple solution which will satisfy. Simple, very simple is start with. Simple means you know that 1 will satisfy, 1 cannot satisfy x, x square, x cube, so on. What is that? y1 equals to x. What is y1 prime? Okay. What is f0x here? Minus x to the power 5. f1x equals to 1 by x. f2x equals to x cube. Right? What do you get finally? U prime equals to, I want the final form of the Bernoulli equation. Fill in the blanks. Fill in the blanks of Bernoulli equation. One by x plus x cube. Check it out. 2x to the power of 2. This side. How to solve this? This is Bernoulli equation. We have done in BTech level. This is Bernoulli equation. How to solve it? How to solve it? We have to get another variable such that v equals to 1 by u and v prime is minus u square 1 by u square u prime. Such that when you put it here, so the rule is that this type you have to put it here. So this u to the power minus 2. U to the power minus 2, this into x to the power 3. Now you have to define a variable such that u to the power minus 2 u prime can easily substituted and it is nothing but v prime. That is the way Bernoulli equation has been done in your BTech level mathematics. So it should be what? Can you tell me? V prime minus or plus? V prime minus or plus? B prime minus. This is minus. If you don't try to remember, just there's a gap. B prime plus will give me the answer. 1 by x 2x to the power 4 minus x cube. Am I correct? Okay. This is your dy dx plus py equals to q term. Integrating factor, you know that. E to the power 1 by x 2x to the power 4 dx, right? Okay. So that you can actually do it. And final answer I will give here. Those things no more. Which is y equals to x into c plus half e to the power 2x to the power 5 by 5 by c minus half e to the power 2 by 5 x to the power 5. That's the final answer. So this is the overall end of the story. So now I will give you one more problem which you can try at home. And what in the exam, what kind of problem can you given? For example, I will give this type of problem. Y squared y triple prime minus 1 by 2. You may not get the complete solution. I want to see what way you can conduct a research to solve the problem and how far you can solve. Like research we do. Research means we are not supposed to solve a full problem. We are supposed to solve a problem on what level you can. I want to see, and based on that you will be given assessment. How much you can approach. This is the problem I want you to solve. Maybe you can answer this question in the quiz 2. Y square y double triple prime equals to minus 1 by 3. I am asking you a question, how to solve this problem. Point is, you may get solution. You may not get solution. On how far you can apply your knowledge and what is the form you are getting. That's my question. I will say question. Attempt to solve this problem. I want to see your attempt. You have the tools with you, like a toolbox. You have the toolbox with you. This is nothing but non-autonomous, non-linear, non-homogeneous system. It is nothing but non-autonomous, non-linear, but it is autonomous, non-linear system. Non-autonomous thing is not there. It is autonomous, non-linear. Okay? So that means we don't have to go about homogeneity in the x, homogeneity in y, all those things. We don't have to do only things to do auto reduction technique first. I am giving the tools. If you do auto reduction, what will happen? Next step. I will tell you that what will happen if you do the auto reduction. It will become non-autonomous system. To try it out. That means when it becomes autonomous, we have to do again homogeneity in x, homogeneity in y. Equidimensional x, equidimensional y. Okay. If you do that, what you will get? I will just tell you the steps. I won't tell you the answer. It is becoming equidimensional in some direction. Then we have substituted. After that, I got again second order autonomous system. Non-linear. Then again I did the auto reduction. Okay? Then I did the auto reduction. Then finally I got something. So I am just giving one of the problems. Let's see who can do it. That could be the exam problem. You don't know. Okay? Next, so we have seen the last couple of lectures. We have done real, it's called that in cricket fast bowling. It's a real bouncer actually went on you on the fast bowling side on the non-linear operator. We have seen that kind of differential equations have actually addressed in the class. It is generally covered at the higher level of mathematics, but I am glad that you could learn something on the differential equation. If now you should not be afraid of it. Any kind of differential equation is given to you, you know how to solve it because we have the toolbox with you and we have seen all sorts of differential equations. Homogeneous, non-homogeneous, autonomous, and the linear and the non-linear. So this type of things were not covered in vector space, because vector space everything is linear. Vector space operator is linear. In the functional space, conductor is differential operator, and differential operator is not linear. Most of the cases, sometimes differential operator is linear, sometimes differential operator is non-linear. And if the differential operator is non-linear, you have to solve it. You cannot say, okay, I cannot solve it. Some of the cases you can solve it, some of the cases you have to go for the numerical analysis part. So we have seen the nature of nonlinear operator. Next thing is that in vector space what we did, after that we went to the eigenvalue, eigenvector problem, right? I am just exactly following the format of vector space. We have done the functional space properties. We have seen the matrix, we have seen the norm, we have seen the inner product space, we have seen the Gram-Schmidt orthonormalization criteria, we have seen 1x x squared the basis, how to get this orthogonal basis. Then we wanted to look at the operator property, which is a linear operator property and non-linear operator property. We found non-linear operators are possible in functional space, which is called as non-linear differential equation, and we are trying to solve some of the non-linear operator problems. So now in vector space we have seen any solution in the vector space can be expressed as a linear combination of basis vectors. Similarly, functional space, any function can be expressed as a linear combination of basis functions. Basis functions are already known, 1x x squared. Are they the good basis functions? In the vector space we have proved that good basis vectors are eigenvectors. Can we have the eigenfunctions? What it look like? What the eigenvalue problem looks like? That means what I am trying to say, in vector space we have A is equals to B, and eigenvalue problem is A u I is lambda I u I. Right? Similar kind of thing it doesn't occur in functional space. So that means functional space we have Lu equals to F. Sometimes we represent as dq by dx square equals to F. Okay? What is the corresponding eigenvalue problem? That's what I'm going to address here. What is the corresponding eigenvalue problem? Any idea? Any guess? Or you can directly solve, say from here, which is Lu I equals to minus lambda I u1. Remember that we have here plus, here it is minus. Why it is minus? I am going to discuss. Why it is minus I am going to discuss. It will take some time for you to know. But the eigenvalue problem, if you look at u which was lambda iu, here it is Lui minus lambda u1. So it is possible to find the eigenvalues in functional space. It is possible to find out the eigenfunction. Remember that eigenvalue, eigenvector is there, or they are there. There must be eigenvalues and eigenvectors for functional space. Since functional space is infinite dimensional vector space, so eigenvector is termed as eigenfunction. So quite often the kind of what we actually have done before getting into the properties of the eigenvalues. There are properties we found. The symmetric matrix eigenvalues are real. Symmetric matrix eigenvectors are orthogonal. How you proved it? Do you remember? How you proved it? How you proved all those things? Symmetric matrix eigenvalues are real. Symmetric matrix eigenvectors are orthogonal. How did you prove those? Adjoint theorem, excellent. So here the next question comes. Adjoint theorem. So that means that adjoint theorem wise, we have inner product LUV, which is nothing but a function, equals to U L star Vx. The question is it the thing? Of course not. This is not valid because we have something called JUV. some extra term is coming here. In adjoint theorem, in vector space, we have inner product UB equals to UL star B. If N equals to L star, you say operator is self-adjoint. Right? Here, the case is not the same. So, when a differential equation is given to you, remember that you need to have boundary condition. At x equals to 0, you say 1, and say u prime x equals to 1, you say 0. Otherwise, you cannot get unique solution. This boundary condition plays a significant role, and this boundary condition generally comes here. This is called as, this extra term is called as bilinear concomitant. This is called as bilinear concomitant. This part I am going to teach very slowly because this is not your 10 plus 2. Very good. So I am going very slowly here. Everything, if you are reading down, you compare the vector space to understand. Vector space you understood everything. So we are going to discuss on what aspects, what will be the conditions for that in functional space operator is self-adjoint. Is it only L equals to L star? If it may so happen that if L equals to L star, this guy cannot be 0. This guy has to be 0 for adjoint theorem. If you remember, in a vector space adjoint theorem is inner product LUB equals to L star B and L equals to L star. It may so happen L equals to L star in an inner product LUB is not equals to L star B. My operator will not be self-adjoint. So in that case, in that case, inner product LUB equals to UL star B plus JUB is there. Some extra term is there. That guy has to be 0. And L equals to L star. Then only you can say operator is self-adjoint. So all those things I am going to address in the next couple of minutes or hours. Okay, so how to now we'll look at the typical adjoint theorem and what are the complicated. So now we have seen the non-homogeneous, non-autonomous operator. So we can say that if I say LU equals to UI is minus lambda I UI, of course a function of x, and what kind of complicated operator you can think about? Non-autonomous operator, of course, you can tell me push you are. That means we can say, okay, I can have x square d to ui dx square plus x duy dx plus ui equals to minus lambda I ui x. This is eigenvalue problem. Right? This kind of operator we have seen, Cauchy-Wallenstein operator, which is non-autonomous but the linear operator. So now the thing is that what I am going to address adjoint theorem only for linear operator. Please write down. Only for linear operator. Non-linear operator is difficult to find. Mostly we cannot get eigenvalue problem. In that case, you have to go for numerical techniques. But the linear operator is possible to use. Is possible to do adjoint theorem. For the linear operator, it is possible to do adjoint theorem. And of course, Cauchy-Wallenstein we have seen in the last class. This is the case of linear operator. This is a case of linear operator. So we can write a generalized eigenvalue problem, which is for this A0x d2 by dx square plus A1x ddx plus A2x. Most generalized way I am saying. It may not be x square, could be something, could be x2, could be x2 power 4, and so on. So L, so this is nothing but LUI lambda UI. I can write this way or I can write this way also. Even that also, even if I write A0, A1, A2, is still a linear operator. Distinct operator, as I said, that adjoint theorem, I am going through particular operator. This could be non-autonomous operator, doesn't matter. Operator could be autonomous, okay. Linear operator, I can do it. Okay? And what is the application for non-autonomous operator? I will get you the eigenvalue problem for different coordinate system. We will go for the Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. So eigenvalue problem. Eigenvalue problems. Number one is Cartesian coordinate system, which is d2u dx square plus lambda u equals to 0. I am saying plus lambda, it's nothing but minus lambda, equal to minus lambda. Simple. Next is cylindrical coordinate system, which is d2u dx square plus 1 by r du dr plus lambda equals to 0. And number 3 is the spherical coordinate system, which is d2u by dr square plus 2 by r du dr plus lambda u equals to 0. Okay. Now you can see that this is dq by dr square. So you can see that this is a1x equals to a1r equals to 1 by r, a0x equals to 1, and a2x equals to not there. So you can see that this type of things will be there for the spherical and even the toroidal coordinate system or the spheroidal coordinate system. This a1, a0, a2, they are very complicated functions. But mostly we will be concentrating in this class cylindrical, Cartesian, and spherical coordinate system. Now the question is how to apply the adjoint theorem for the functional space. Any questions? How to apply the adjoint theorem for the functional space? How to apply adjoint theorem for the functional space? Side LUV. What is our target? We have to get U L star B plus JU. Remember that LU typically d2u by dx square. L star also could be like d2 by dx square something. That means if you look at from this, the higher order derivative of u will go to a function. And function will go to the higher order derivative. Am I correct? Here derivative was second order. Here it is function. Here derivative is not there, function. It has become higher order. So here we have to do integration part by parts in a judicial manner. So what do you have to do? DUV is formula. You have to remember, which is u dv dx plus v du dx. What actually happens if you look at, you may be having this kind of term in one side. V du dx equals to, you can write as ddx of uv minus u dv dx. These kind of things are very easy. We have done in the class 2 calculus. That means picking up u and v are very important. Picking up u and v are very important. If you look at these things almost like similar to this, it is v and du dx going to do something. So let's look at, so entire adjoint theorem, I can tell you adjoint theorem is easier for functional space compared to vector space. Vector space, you remember many things. Functional space, if you remember these two, your adjoint theorem will be solved. Let's look at the adjoint theorem for our problem. Our problem L is d2 by dx square. Okay, the kind of problem what we are going to solve, our eigenvalue problem, which is d2 by dx square minus lambda u, boundary conditions q0 equals to 0, u1 equals to 0. Always we should have, when we have the functional space problem, we have a differential operator, need to have boundary condition. If you don't have boundary condition, you cannot get any solution. If you don't have boundary conditions, you cannot get any solution. Right? If you don't have boundary condition, you cannot get any solution. So, let's look at the adjoint theorem for the functional space. Linear product LUV equals to integral 0 to 1. Domain is defined 0 to 1. L is what? d2u by dx square. V dx is so simple. Nothing is there. Remember that you need to have this type of term. That means immediately you can write this as du dx, v dx. Now you tell me which will be u, which will be capital V, which will be capital U, which will be capital V. Which is, what is this? Capital U, and this is? So you have to write down, assume capital U as du dx, capital V as V. Next step. So ddx of u, du dx of capital into V, which will be ddx of uv minus u dx. So can you please tell me what will be my terms? ddx of u is what? Capital U is what? du by dx into v minus du dx, dv dx, dx. Am I correct? So next step, 0 to 1, dvx, du dx, v dx minus 0 to 1, du dx, dv dx, dx. This differential ddx dx we will go, and it will become differential of du dx and v, and you can write this as du dx v 0 to 1. Am I correct? Yes? Yes or no? Yes. And then minus 0 to 1 du dx, dv dx, dx. Remember that we have to go for this operation as long as you are not getting d2v dx square. That means this guy's derivative should be in the higher order. So in that case, again you have to apply this formula, and you tell me which will be u, which will be v. Which will be u, which will be v. Remember that depends on this quantity. If you look at, if you remember v du dx, by doing this, we are increasing the derivative order of this, right? This is going as boundary term. It's like a boundary term. But you are actually getting, if you write v du dx, you are actually getting higher order. So based on that, if I look at which term will be u, which term will be v, which will be giving you the idea. What will be that? What is your u? What will be v? d by, what is that? dv by dx, and then u will be? No, u. See, remember that we are applying v du dx formula. So basically, dv dx is already there, right? So this will be acting like your du dx. This will be acting as v. So what will actually happen if you are not able to understand? So what you can actually write this term, we can write this as du dx, capital Du dx, and this term is capital B. U as capital B. This is better. So U as I can small u I can write as capital B, and dV dx I can write as capital U. Is that okay? Yes or no? Then what you get here? You get dV dx into U. Am I correct? Sorry. U is actually small b. Am I correct? Yeah. U is small b. What will you get? Final answer? Du dx b 0 to 1. Next step. Any confusion here? You catch me here. Any confusion here? So far everything is fine, right? Up to this everything is okay. Remember that you have to use this formula. You have to use b du dx kind of formula. And remember that if you basically this should be your b term. This should be your b. This should be your b term. And this is already there, u term. So that is fine. I think that is already fine. Capital B term. So please correct it. dV dx and u is capital U. Now tell me, what's the formula? Integral b du dx equals to ddx of ub minus u dv dx. Now you should tell me by blindly what is that ddx of small u dv dx, right? Integral 0 to 1 ddx of small u dv dx plus 0 to 1. What you are getting? U means what? Small u. dv dx means d2v by dx square. Am I correct? d2v by dx square. Dx. Is there any doubt? I have done the maximum level I can do. This level, any book, no books actually are there in this level. Understood? Amit, you are lost, I guess, completely, right? What we are trying, this maximum thing I can actually tell you in the class. This is the maximum level. Remember that we need to increase the order of the derivative. So the term what we are increasing, we have to blindly keep capital B, and other term is u. So dv dx is capital B is nothing but your b dv b. Another term is small u. Okay, and in that case, capital B du dx is nothing but ddx of ub minus u dv dx, and you have ddx of u dv dx u square by dv dx square. Concept is clear? Any doubt from anybody I can address once again. Any doubt from anybody I can address once again. Any doubts? Any doubts from anybody? Yes? So what term will be getting finally? Inner product LUB equals to du dx b 0 to 1 u dv dx 0 to 1 plus 0 to 1 u d2v dx square. I am assuming everything is okay so far. Everything is okay? Any doubts? No doubts. This is known as bilinear concomitant. The extra term, we didn't get this kind of terms in vector space. Now, if the operator is self-adjoint operator, you need to have adjoint problem. That means, adjoint problem, we have seen in the Fedorov quadratic theorem. What is that? d2b dx square is your lambda minus lambda b, adjoint operator problem. Lambda prime b. You need to have boundary condition for b. I am putting b0 equals to 0, b1 equals to 0, such that ju equals to 0. Is it coming? v1 equals to 0, I am putting v0 equals, so this term is going to be 0. u1 and u0 both are becoming 0 in the original differential equation. So if the adjoint problem is defined such that your JU, your binomial concomitant is 0 and L star is d2 by dx square equals to L, which is also d2 by dx square, in that case your operator has become self-adjoint operator. In that case your operator has become, so in this case based on the adjoint problem, so that means when you have the adjoint operator, not only your operator is self-adjoint L equals to L star, also your boundary condition. That means your problem is d2u by dx square. This is your operator. The boundary condition, I can write this as bu equals to 0 in a generalized format. B is the boundary operator. B is the boundary operator. How to write boundary operator problem if you want to visualize? u1, u0, 0, 0. Am I correct? Boundary operator is a vector operator. Similarly, adjoint problem. d2b dx square, b0 equals to 0, b1 equals to 0, and you got b star b equals to 0. This is L star b. And here you can see that 1 0 0 1 b1 b0. And what you can see for adjoint operator problem, L equals to L star and b also equals to b star. Then the operator is self-adjoint. Then the operator is self-adjoint. Yes or no? And you can see that because of this your bilinear concomitant is becoming 0. And what are these? They are the adjoint boundary condition. An adjoint boundary operator, b star and b becoming same. Okay? B and b star same, L equals to L star same. That will make bilinear concomitant 0, and based on that you can say your operator is self-adjoint. Based on that you can say your operator is self-adjoint. That part is clear? Now how to make it self-adjoint? So b equals to b star, L equals to L star. With that your JUB equals to 0, and in that case your operator has become self-adjoint. So you have done the derivation with a simple operator d2 by dx square. Now we go for the generalized non-autonomous operator. I will start and then you can continue tomorrow. I'll just start for some few minutes and then stop for today's class. So linear non-autonomous operator, which is a0x dx square plus a1x du dx plus a2x u equals to minus lambda a dx u. Most generalized way to represent an eigenvalue problem. Most generalized way to represent the eigenvalue problem. The question is verify the adjoint theorem. Question is verify adjoint theorem. Verify adjoint theorem. The question is verify adjoint theorem. How to start? Inner product LUV, which is my domain is, we can say A to B, most generalized. I am saying my domain is A to B, which is A0x d2u dx square plus A1x du dx plus A2x u v dx. What is my term? Integral A to B A0x d to u dx square v dx. I'm just splitting all the terms. A to b a over x du dx v dx plus a to b a to x u v dx. The first term, second term, and this is the third term. Remember that we have to express in terms of u L star v and L star to this sort of d2 by dx square kind of term. Okay. Now we have to see whether this operator is self-adjoint or not. Question is a linear operator. Is it self-adjoint? That's the question actually coming in our mind. So we have to look at each of these terms. So let's look at the first term. Let's look at the first term, term 1, which is a to b a0x d to u by dx square v dx. First, we have to decide which is u, which is v. Remember that you have to apply the formula integral v du dx equals to d dx of uv minus 2 dv dx. That's the formula we have to use. The formula we have to use is v du dx equals to d dx of uv minus uv dx. Okay. Which will be your u? First you have to decide your u in the bracket, then only you have to proceed. Which will be your u? Capital U is du dx and capital V is, what is that? A naught x equals to A naught x into V, because you cannot remove, you cannot omit anything. Everything has, if this constant is okay. This is not constant, the function of x. How can you remove this? Okay? You are very correct. Next step you tell me. V dx of du dx a0x v dx minus du by dx ddx of a0x into v dx. Next step is du dx a0x v a to v. Next step is minus a to v, which is x, which is u, which is v. Remember that this derivative has to increase. That means this has to be v. So this entire thing has to be v. Okay, and this is of course u. So what is my next step? ddx of next step ddx of what is that? ddx of a0x v into u. Am I correct? Minus dx, it should be plus integral a to b, which is u d2 by dx square a0x v dx. Am I correct? Yes. So what actually will happen? Du dx a0x v a to b, then it will be u v dx of a0x v a to b, then integral a to b u d2 dx square a0x v dx. So like that you go by term 2 and term 3. You tell me the answer tomorrow what you are getting, whether the operator is operator A equals to L star. I am not saying the self-adjoint. Is L equals to L star? That's my question. Although the operator is linear. Thanks for your kind attention.